This is lesson 1 of unit 12. In this unit, we will talk about liquids and solids. In the previous chapter, we talked about gases, and here we're going to talk in detail about the properties of liquids and solids. Much more about liquids and much less about solids, but we'll mention both of them as we go along. Now, the first thing we'll do is recall in the previous chapter when we talked about gases, we said that gas particles don't attract or repel each other. There are no forces between gas particles. They just kind of bounce off each other and keep going. So they don't have anything, they don't pull on each other. This was part of the kinetic molecular theory that described gases. However, in liquids and solids, that's exactly the opposite. In fact, this is what distinguishes liquids and solids from gases. The presence of these forces. These are going to be called intermolecular forces, and we'll define these in a minute. So this is a huge difference. That's why we're spending two different chapters. We've split them up into two chapters. Now, intermolecular forces are actually a type of force between molecules. So here we have two types of forces. They kind of look similar, but if you read, the first portion of it is what's different. Intermolecular, and here intramolecular. Intramolecular, intra means within, are the forces within a molecule. So here's a molecule of HCl. This is hydrochloric acid. The force that holds two atoms together, the hydrogen and the chlorine, is called the intramolecular force. This is actually a chemical force. The force that holds the two molecules together, this force here with the dotted line, is the between molecules. This is the one we're actually going to be studying in this whole chapter. And notice that the solid line and the solid line is a stronger force. This is stronger. And the dotted line indicates that this is a weaker force. It's easier to break, is the idea. So we're going to be looking at these intermolecular forces in this chapter as we go along. Now, real quick, another word about this. In a chemical change, intramolecular forces or bonds are breaking. So if you take water, in both these examples I have water. If you want to split water into hydrogen and oxygen, hopefully you've seen this done in class, you have to break the chemical bond, the intramolecular force. When you're boiling water for some tea, the intermolecular forces break. It's the bonds between molecules. You're not changing water into a new substance. And this is oftentimes a misconception. Students think that whenever you're boiling water, water turns into oxygen gas or hydrogen gas. This is not true. It's just water now in a different state. So this is a physical change. Again, intermolecular forces are what we're studying in this chapter. So we'll study physical changes, not chemical changes. There are three types of intermolecular forces, and we'll study each one of them in detail. These are called van der Waals forces, after Mr. van der Waal that first came up with them. These are very important forces that describe the physical properties of chemicals. The first one is dispersion forces. The second one, dipole-dipole forces. And the third one, hydrogen bonding. We'll actually take a look at each one of these in detail as we go along. So let's get to the first one, which is London dispersion force. London dispersion force. That word dispersion actually means something in here. And it's the intermolecular force between nonpolar molecules. We'll review what nonpolar means, but in the meantime, whenever two molecules come close to each other, their electron clouds repel and push each other away. So this electron cloud here and this electron cloud essentially push each other away. And so on the left side, the electrons essentially go on the left side. They're pushed away from each other. And then what you create is you create a slightly positive side and a slightly negative side in both molecules. This molecule gets the same thing going. And then you've got this force, this intermolecular force. Note the dotted line. This is the momentary charge. This is momentary, meaning it's not permanent, created by electrons moving in an atom. So in fact, what you see, this cloud, remember, are electron clouds. So this is momentary. You'll see it's the weakest of the forces. That's the first one. Real quick, let's review what we mean by polar and nonpolar molecules. Remember, a polar molecule is a molecule that has uneven charge distribution, which means it creates a dipole. Now, a dipole is essentially the difference between the bottom and the top of the molecule. So when you have uneven charge distribution, you have more electrons up here, we'll say. You have a more negative charge, since electrons are negative. You have less electrons in the bottom, a more positive charge. And that's why the polar molecule is polar, because of this uneven charge distribution. A very famous molecule that's polar is water. And actually, you're looking at water's structure in both of these cases. On the bottom, you have the hydrogen. On top, you have the oxygen. This is really due to the fact that water is bent. Recall, when we drew water, if you remember, water was always drawn like this because of its bent structure. Whereas a nonpolar molecule is one that has even charge distribution. So a famous one is CO2. The way we drew CO2, if you recall, was like this. You don't have to recall how to draw these. We'll help you with that. And so you have the same type of charge on the left as on the right of the molecule, and the molecule is evenly distributed. So these polar molecules, we refer to them as sticky because they have, it's like a little magnet, miniature magnet. And nonpolar molecules are not sticky. Think of it that way. So the second force is a dipole-dipole force. If you have yourself polar molecules, this means they will attract each other. So you see the permanent polar positive side here attracts the permanent negative side, and the negative the positive. You can also have molecules attracting left to right, where this negative and this positive make them attract. So these molecules stick to each other and create a liquid, for example. This is with polar molecules. The last bond, the third one, the hydrogen bonding, is actually the intermolecular force created when hydrogen is bonded to three elements: fluorine, nitrogen, and oxygen. This is actually an extreme version of the dipole-dipole force, a very strong force comparatively to the other ones. This, as you'll see, is famously the force that holds water molecules together, hydrogen bonding. Now, we're going to explain this in a little more detail, and what happens is anytime you have a very electronegative element, in fact, let's take a look at the next slide. This will make a little more sense. The question is, why does this relate to, why is it present only in these three elements? Recall that electronegativity is the measure of how strongly an element pulls electrons. So anytime you have fluorine, fluorine is actually the most electronegative. He is the electronegativity king. So whenever fluorine is bonded to any element, fluorine will pull the element's electrons off of that element. So here, fluorine is bonded to hydrogen. Fluorine.
Interruption at this time. I ask that you check.
The fluorine will again pull the electrons toward itself, and it pulls them off so much off the hydrogen that the hydrogen gets essentially exposed. It's a bit embarrassing, but the hydrogen, because hydrogen has only one electron. Remember, hydrogen has only one electron here. The hydrogen has nothing else to protect its nucleus, and it becomes a very positive charge. So again, this is why hydrogen bonding occurs with the most electronegative elements, because they're able to pull the electron almost completely off of hydrogen, exposing the positive nucleus. So it doesn't really work with any other element because they're not strong enough to pull the electrons off of hydrogen. And that's why it works with these three elements. Okay, so to review these three forces, the first one, we're going to flip them. The hydrogen bonding is the strongest of the three. It's a strong force present only in these three cases. You have to have hydrogen bonded to one of these very electronegative elements. The second one, the dipole-dipole force, is a medium force present in polar molecules. You have to be a polar, a permanently sticky molecule. And then London dispersion forces are the weakest of the three. These are present in nonpolar molecules, as well as all molecules. This is because all molecules contain electron clouds that can be dispersed. So this is actually very important, that London dispersion forces are present in all molecules. Why don't we try to apply this concept to a few example problems. So take a look at example problem 1. And here we're asking, tell which intermolecular forces are present between the molecules. So what you have here, and I'll draw out for you the Lewis structures. Remember, these are called Lewis structures. The first one here looks like it's evenly distributed. The electron cloud looks the same everywhere on the molecule. This means it's nonpolar. This means the only force that's going to be present will be London dispersion. Now, the second one, this is actually a polar molecule because the hydrogens are unevenly distributed. You can think on the top of the molecule, there's an extra electron pair. So this will be a polar molecule. Now, because it's polar, you have present dipole forces. You get dipole forces, but you also have London dispersion forces. In fact, all molecules have London dispersion forces, so that will be automatic for everything. In the case of NH3, you have a very similar picture as you do in pH3. However, nitrogen is one of the 3 most electronegative elements. Remember, F, O, or N, nitrogen is one of them. So nitrogen will be able to pull electrons completely off of the hydrogen, creating a very, very positive side in the hydrogen. This means this has hydrogen bonding. Now, it also has dipole forces.
Teachers, at this time we're going to secure for our drill. Thank you so much for your cooperation.
Dipole forces. Because, and we can call these dipole like this forces. And then this also has London dispersion forces. Again, every molecule has London dispersion forces. So these are the possible forces for these molecules. So go ahead and think through this. The concept is very important, and we will apply this concept to other physical properties.